Morning, everyone. So we're going to transition to Bruce's number one enemy, energy efficiency. Good. We're in agreement. We're in complete agreement. Let's skip over this stuff. So we've seen this chart twice now from both Bruce and from Larry about the overall GHG impact that comes from buildings. It depends on how you want to analyze that. The California Air Resources Board kind of slices and dices it in more granular detail, so they break it up between residential buildings, commercial buildings, the electricity sector, which goes to all buildings, as well as the industrial side of things. And then you can also look at it at the end use perspective. So on the right is a chart that was put together by NRDC and a number of other folks looking at the end uses of emissions, and this is just around operating emissions. So I want to clarify that, the 40% number that you guys were showing before, that's inclusive of both operating and embodied. This is just operating emissions in the state of California. But what you see is about 10% of emissions in our buildings comes from electricity, and then around 15% is direct emissions, and that's essentially the burning of natural gas in our buildings. And that's also inclusive of the leakage associated with natural gas, getting it from extraction through the pipelines and into the end uses within the building. So we've mentioned before the electricity is getting cleaner. There's a number of initiatives in California to help reduce the carbon content of electricity. And that's why this looks pretty nice. If you look at this chart here on the left, we're looking at the total amount of emissions that come from buildings. A large percentage of that is from electricity, but again, that's because that electricity elsewhere in the country has a lot of coal or natural gas associated with it. And then a portion of that is the natural gas actually used within that building. In California, things look a lot better, again, because a larger percentage of our electricity comes from renewable sources. So about half of the emissions in a building per unit of energy is coming from the electricity, and then another half is coming from the natural gas. And the Bay Area, and this is alluded to before, we have a pretty moderate climate in the Bay Area, so we're not going to have as much air conditioning especially. So the overall impact of electricity in our buildings and the carbon content associated with that is a little bit less than it would be throughout the state. But the natural gas number stays pretty much the same. And this kind of, you see this stay the same across California and across the country, and that's really water heating and space heating predominantly, maybe a little bit of cooking, maybe a little bit of laundry drying. So here's the different end uses in our buildings that use natural gas. And there's a number of technologies that we can replace those natural gas equipment with that would reduce emissions, predominantly heat pumps, but there's a number of other technologies that could do it. So about 50%, just under 50% of the natural gas we use in our buildings goes to water heating. So that's water heating for showers and faucets and whatnot. There's a number of heat pump products out there that can address that load, and we'll talk about that a bit more. 37% of the gas we use in buildings goes to space heating. Again, there's a number of low carbon electricity equipment that we could use there. About 4% actually goes for pool and spa heating. This is mostly single family homes, but also multifamily and motels and hotels. There's a great heat pump product out there, actually incredibly efficient, much more efficient than gas, that we could use to heat the water in our pools, or use solar thermal for that, or just don't heat the water in the pools and only swim in it in the summer. Dryers, laundry dryers have a number of technologies out there that can use electricity. And then cooking. And this one's kind of contentious because people really like gas cooking. But there is a number of electric cooking appliances out there. Obviously, the one we're all used to is just a traditional electric resistance stove, either with the coils or the glass plate on top. And no one really likes cooking on those. I don't like cooking on those. It takes a long time to heat up, and you don't have very good control. And that's why people tend to like gas. How many folks have heard of induction cooking? Awesome. Preaching to the choir here. So yeah, induction is a really cool technology. If you've used one before, I'm sure you can attest you have great control. equal to or better than you might have with gas. So there's technologies out there that we can begin to incorporate in our buildings that use less emissions than the natural gas equivalent would use. So here's a chart I borrowed from my friend Pierre at NRDC, and this is comparing different water heating technologies. And so it's a little bit busy, but this black bar here is for an electric resistance water heater. And so that says a COP there. That stands for a coefficient of performance. That's just a technical term for efficiency. So you can have an electric resistance water heater. That's your kind of minimum efficiency water heater. That's about 96% that uses electric. This blue bar here is a gas water heater that most of us are used to, that we would see in our single family home, like the tank type water heaters. That's about 60% efficient. That's code minimum right now for gas water heaters. We're allowed to get away with 60% efficiency. You could go high efficiency on a gas water heater, like a tankless technology. That's about 95% efficient. Or you can do an electric heat pump water heater, which actually has an efficiency of about 270%. And then on the bottom here is the percent renewable electricity on the grid at a given time. And so on the left of the scale is 0% renewable electricity, so, you know, a fully carbonized electricity. And then on the right is a completely renewable or completely no carbon electricity. Yeah. So I'm not going to go in there because I'll lose everyone. But heat pump technology actually can have efficiencies 200% up to 400 or 500%. And the way it does that, it actually moves heat from the ambient air into whatever medium it's trying to heat. So for a heat pump water heater, it's a technology that moves the ambient heat in the air, and it uses electricity to move that heat and pushes it in the water. It's essentially what your refrigerator is. So your refrigerator is moving the heat out of the refrigerator and dumping it into your house. It goes the other direction. Exactly. For every 1 watt of electricity that your compressor uses, you get 2.7 watts of heating energy. Exactly. And so, you know, this could be just based on like the renewable portfolio standard of our electricity system, or you could look at the marginal amount of emissions at any hour on the grid, right? So in the middle of the afternoon when we have plenty of solar, you know, this number could be up to 60 or 80% renewable. But at peak loads or at night, you know, we might be looking at 0 to 20% renewable electricity at that given hour. But even at a 0% carbon or 0% renewable electricity, a heat pump water heater has less carbon. On the left is the amount of carbon per unit of energy, has less carbon associated with it than either the high efficiency gas tankless or the code minimum gas tank type. And then as you get more renewable, then it looks even better, right? And to the point where even the really low efficiency electric resistance water heater has less carbon in it. And what's nice about electric resistance water heating or space heating, there's no refrigerants in it either. We'll talk about that in a bit more. Oh, right now. So we can't ignore refrigerants, right? And Bruce mentioned this before. Refrigerants are important in a number of our building materials. And heat pumps, air conditioners, refrigerators, all of those have refrigerants in them. And so those refrigerants have a high global warming potential, or GWP. So carbon dioxide has a GWP of 1. These refrigerants have, you know, hundreds of thousands of times more global warming impact than 1 unit of carbon dioxide would. And so the typical heat pump that's being used for space heating, it uses a refrigerant called R410A, which has a global warming potential of about 2100. Most of the water heaters are down here, still pretty high. They use what's called 134A, about 1400 GWP. So we still have some issues here. You know, at some point, I don't know if all of it's going to leak, but a percentage of it's going to leak. And so talking about the life cycle analysis that Bruce mentioned before, what would be really neat to see is assume a business as usual, or maybe a best case, worst case, about how much of that refrigerant leaks or is captured relative to the efficiency gains and the reduction in emissions you get. And what's the life cycle analysis of that, even with these pretty poor refrigerants that we're using today. California Air Resources Board has a number of proposed regulations coming online to require manufacturers to reduce the global warming potential of their refrigerants. And so in 2023, at least for air conditioners, they're proposing 750. So we're getting lower, but it's still not as low as we need it to be. There are a couple of technologies out there that are really low already. So I mentioned before, carbon dioxide has a global warming potential of 1. There is heat pump technology out there. For example, Sandin is a manufacturer that makes a water heater that uses CO2 as its refrigerant. So we got a really low global warming potential already. Another interesting one that's being analyzed and researched and developed is using the refrigerant name is R290, but it's actually just propane. So you can actually use propane as a refrigerant. Has a pretty low global warming potential. What's the problem with propane? It's pretty dang flammable. So there has to be a lot of work being done to see if we even want to bring that type of refrigerant into our home, but it is an option. So there's regulations coming online that are going to reduce this GWP, and there's going to be a number of technological advances as well. And reducing the overall system size that you need for either water heating or space heating means that you can use less refrigerant, right? A smaller system, and Bruce also mentioned this, like a smaller air conditioner is going to have less refrigerant in it. And so if I build smartly, I use low carbon envelope material and insulating material so that I don't actually need that big of an air conditioner or that big of a heat pump. Or I'm smart about how I build my water heating system so that I don't need as big of a water heater. That uses less refrigerant, and thus the potential for leakage could go down. You could get to the point, especially with space heating, that you make your building so awesome, so well insulated with low carbon insulating material, really good ventilation, that you can get away with heating with just an electric resistance space heater, just a baseboard or a cadet, which has no global warming potential at all, really cheap to install, really easy to operate. Good question? There's still a lot of unknown about what's coming out with those regulations. There may be someone in the room that, either from BACMUD or others, that might be better qualified to answer that. But TBD. The whole country is watching it, right? As California does, the rest of the country does. And so manufacturers are going to need to redesign their equipment to work in California. And it's essentially going to be the equipment they sell throughout the country. So there's a lot of eyes on what those regulations are going to be. So I don't know for sure to answer. So not all energy efficiency is equal. And this is really important. NetZero was a really effective policy tool and design tool to get us where we are at today, but there's a problem with that word net, right? Whether I'm using gas and I'm offsetting that on an energy basis with solar systems, or all of the electricity that I use in the winter at night, yes, my solar system during the day is creating the equal amount of electricity and sending it to the grid, but carbon doesn't behave, doesn't behave with the laws of Excel spreadsheets, right? If I'm using high carbon electricity at night, that carbon is going into the atmosphere, regardless of what I do during the day with my PV system. So it's really smart to start thinking about when we're using our energy. With gas, it doesn't really matter. It's always going to have high carbon in it, regardless of what hour I use. But with electricity, it's really important to know which hour of the day and which month of the year I'm using that electricity. So this is a really cool heat map that Martha Brook made from the CEC. There's a lot going on here. On the left is 2019, on the right is 2030. This is each hour in the day, so midnight down to 11 p.m. And then this is each month of the year, so January over to December. So where we're at today, the spring in the middle of the day is a very low carbon electricity time. It's because the sun's out, but we don't have a lot of air conditioning going. So you don't need to turn on the gas peaker plants. But as you can see at night, especially late summer and fall and in winter, our electricity actually has a lot of carbon in it because obviously the sun's down, right? And in 2030, there's technologies that hopefully can improve that. We're going to be looking at batteries and hydro storage and other technologies that might reduce the amount of carbon in the electricity grid. But it's really important to use that electricity at times when the carbon content is low so that we aren't actually sending emissions into the grid or into the atmosphere. I'm sure everyone's seen this duck curve before, right? This isn't new to anyone. But basically, in the middle of the day, there's a lot of solar on the grid, and so the actual net demand on the system for fossil fuel generation is really low. So we can start thinking about doing interesting things with our water heaters and with our space heaters so that we're using as much energy as possible in the middle of the day when electricity or when carbon content is low. You know, maybe we heat our water heater to a higher temperature in the middle of the day, right, to maybe 140 degrees, way hotter than we would ever need for a shower. But that means then when the sun goes down, my electric water heater doesn't actually turn on. I'm able just to pull hot water off of that water heater overnight. Maybe I can ride all the way until the morning, till the sun comes back up, and then I reheat my water heater then. And same thing with space heating controls, and the smart thermostats and stuff are getting around that as well. So this is just sort of an illustration about doing it right when you're installing electricity equipment or energy equipment in general. So, you know, if we're just looking at operational efficiency, so just the emissions of that energy use, if I install a high efficiency piece of equipment the first time, my emissions are going to go really low and they're going to stay pretty flat throughout the life of that equipment. We're proposing 20 years here. But, and we see this all the time on projects, you know, value engineering comes into the picture and they start looking at lowest cost type of equipment, and that equipment may be lower efficiency, or it may be decent equipment that's just installed really poorly, right? And so what happens then is the emissions are going to be higher for that piece of equipment. And then let's say in 10 years, either by carrot or by stick, you know, that building then needs to replace that equipment to use less energy. They'll reduce it at that time, and now they got down to a lower operational efficiency level. But when you start to think about the embodied carbon of that equipment, then it looks even worse, right? So maybe, and again, this is just sort of illustrative, you know, when I put that new piece of equipment in, maybe it had more embodied carbon in it because it's higher efficiency. It's got aluminum or steel or whatnot. So the initial embodied carbon might be a bit higher, but then if I did it right and I did a high efficiency piece of equipment today, I get that bump at the beginning and then it goes down and stays low in its operational efficiency. But if I need to replace it in 10 years by carrot or by stick, then I'm going to have another hit when I have to put in this new high efficiency piece of equipment. So when you look at those on a cumulative basis over the next 20 years, you actually see I get two jumps, one from having a higher carbon content, more energy use associated with that mid-efficiency equipment or poorly installed equipment, and then I have to replace it again. So really, this is just reinforcing the importance of doing it right the first time, focusing on high efficiency equipment and a quality of installation. It's really important. You know, if something's installed poorly the first time, it's going to need to get replaced or repaired before the end of its useful life. And then going back to focusing on gas versus electric, you know, there is such a thing as energy efficient gas equipment, but if gas equipment is installed today, either in a retrofit project or a new construction project, and then 10 years down the road, I think, Larry, you showed the graph of if we do stuff aggressively now, or if we wait and go, oh, geez, we have to really get aggressive with this in 10 years, all that gas equipment is going to end up being a stranded asset. And so there's embodied carbon impact of that, and there's cost impact of that. So when gas equipment is installed in a building for new construction, there's a lot of gas pipes. They're going to go from the gas meter to all of those end uses. That's a cost, and that has embodied carbon in it. If you're going to connect to the utility main from the street up to the meter, that's expensive and has a lot of embodied carbon in it. And so both of those cost money, and both of those, if we're being smart about it and planning ahead for the next 10 or 20 years, if I just pull that out of the project entirely, I get operational efficiencies, construction efficiencies, embodied carbon efficiencies. Gas equipment is also going to have combustion venting, so it's burning gas, so I got to put that stuff somewhere. So you're going to have metal or PVC or stainless steel venting to remove that equipment or remove those combustion gases. And I have to make a whole bunch of holes in the envelope, both for this venting to go up through the roof or through the wall, and then for all these gas pipes to come in through the building and through the apartments or through the home. So, you know, some things we can kind of cheat on a little bit, like electric lighting. You know, lighting is going to need to be replaced every 10 years maybe. So if I make a mistake now, I have a chance in 10 years to replace it. Water heating, space heating, you know, that stuff maybe lasts 10 or 20 years. We don't have that much luxury now to make mistakes, but at least I get some chance in 2030 to fix it. But when we're looking at building correctly a whole structure, we get 1 or 2 shots in the lifetime of that building to do it right. So if we don't do it right today, we're going to miss our chance, and we're not going to be where we need to be in 2030 or in 2050. And again, factoring efficiency into all of this, if we can be smart about how we build the structures so that we reduce the loads, we can get really small equipment, potentially low refrigerant amount or no refrigerant. So smart envelopes, smart ventilation systems allow us to use smaller, low cost, simpler equipment. Same thing for water heating. If people actually think about where I run my pipes and the end uses that I have on the shower heads or the faucets, that means I could use a smaller water heater. And then that also means if I'm trying to go net zero and I want to use a solar PV system to offset all that energy use, if I was really smart about how much energy the building actually used, I can install a smaller PV system which has lower embodied carbon in it as well.